Hi, I'm Jason Harris. I'm a senior front-end developer. Today I'm going to be talking about advanced typesetting in Mathematica and how you can create your own customized notations in Mathematica to affect whatever notation is in your individual field, be it chemistry, physics, math, computer science, or whatever. We'll be able to extend Mathematica with new notations, and you'll learn how to do it in this workshop. Okay, while we're waiting, I just wanted to point out that you might want to go, this is going to be an interactive sort of workshop, so if you want to follow it, the notebook is already available on Pathable. If you go to this particular session, click on that link right there that's really small, and it will download the notebook onto your laptop, and you can follow along with some of the examples as we actually go. So probably want to do that. And I think my time has already started. So I'll kick off. Welcome to this workshop on advanced typesetting. So this will follow on to some degree from what Itai sort of said, and it'll probably go into a bit more depth about some of the topics that he went quite fast over. So this talk, it's going to explore, the whole goal of this talk is for enable you to be able to actually enter your own notations in Mathematica and do computations with them. We don't just want it to look pretty, we want to be able to do computations. And so, of course, math is big. There's many fields out there. We're never going to be able to build in everything that you need, so it's very important for you're in physics or chemistry, computer science, whatever. You'll have some notations that you work with. You want to be able to enter those into Mathematica Notebook and do computations with them. You want them to be live and working. That is the goal of this sort of session, and indeed of typesetting in Mathematica. And so this is what we'll attempt to go through in a reasonable, hopefully interactive way with you here. Okay, so this talk in particular will cover boxes and the representation of typeset structures. I'm going to talk about make boxes and make expressions. And so these two functions enable the front end to talk to the kernel back and forth. And so by overriding these functions, we can enter and we can affect our own new notations. I'm going to talk in detail about template boxes, as Itai has mentioned. I'll talk about the notation package and how you can use that in an easy way to create your own sort of notations. And then I'll talk about style sheets, how to package them up, as Itai talked on, and then miscellaneous topics. Okay, so let's restate our goal here. Our goal is that we've got some, for instance, if you've got some A partial. In physics, that might be an A diff operator. And so we want to make that work. Or even something like escape, PD, escape. Not that. Different angle, escape, PD, escape, control underscore here, and make that a plus of like something like x cubed. Right now, Mathematica doesn't understand that. But we want Mathematica to be able to actually, maybe in the end, take that to a PD plus of x cubed, something else like that. So there's the normal form that we've got of these boxes here, and Mathematica doesn't understand it. What we want is it to be able to, Mathematica to be able to use this PD plus internally, and then of course, you know Mathematica, you can make your own pattern matching, rewrite rules, and so on to make PD plus do something that you want. So the goal was to be able to take some input like this and be able to make it internally work like that. Okay, so let's talk about boxes a little bit. So Itai mentioned this, and he's gone over it reasonably quickly. If we take a look at some box here, to actually look at the box expression underneath, there's this show expression. Very important, you should learn it, know it, Command-Shift-E. And so if we take a look at that expression, you can actually see the underlying boxes. Here, this x cubed right here is actually a superscript box. And I can actually even edit the actual boxes themselves, Command-Shift-E again, back and forth, Command-Shift-E, and evaluate it, and we get x to the fourth plus 2. So I can edit the boxes, I can edit our expressions in normal Mathematica. You're all very used to that. I can edit the underlying boxes to do the exact same thing. And of course, when I type some sort of complex integral like below, you probably all know that you can type these characters. If not, they're on the complete characters palette. And so right there, that's just an integral character. Once I get a subscript on there, we see that is indeed a subscript box. And of course, if I get the other limit there and get an escape, infinity escape, we can see that's a sub-superscript box, and so on. And so I can type the rest of this integral to be able to do things and make computations with it. Okay, so let's take a look at this in what goes on underneath. And to do this, I'm going to be using two dynamics. And so if you don't know too much about the dynamic system, it allows us to sort of link the front end and the kernel here. And this input field of a dynamic of the boxes means as I type in this input field right here, I type stuff, it will set the value of the boxes to the input we've got in boxes continuously. And this output just shows it what this value the boxes is. So if I type A plus B, I actually see what is the underlying boxes the front end's actually using. And so it's using this row box of A plus B, and here we have times C. And we've noticed already that the box parser has grouped our expressions. We know that B times C is a tighter precedence, times has a tighter precedence than plus, and so we see this grouping already in our structures. Okay, and so now as we type some expression here, escape and escape, I start seeing there's a subscript box, and here now I see a subsuperscript box, and I see this complex infinity. I see this double struck E, this exponential E. I see another superscript box, the minus X, and I see a superscript box, the row box, and the double struck D, escape. And so we finally see, as we've entered all of this various bits, this is the underlying expression. So this is basically what the sort of front end is, editability. As I type stuff into Mathematica, I see there's the underlying box parser. This is exposing the beating heart of the underlying box parser, how it will form and reform the various expressions to have the boxes that represent what we've typed. Okay, so that's about boxes. And you might think, well, okay, that's just sort of some typeset. We've got some mathy bits, but not everything is boxes. But if we take a look at some random expression here with lines, and we can move it around and extend them and do stuff with them, is that boxes? Well, indeed, if we take a look underneath, it's a graphics box of a line box. And so graphics themselves are boxes. And here we have a Bezier curve box, and you might think, well, that's probably, it's a smooth spline. But no, indeed, it's a Bezier curve box with line boxes and point boxes and so on. So all graphics are also boxes. And indeed, our controls, if we take a look at them, we've seen interface construction and styling. If we have a style, it turns out to be a style box. A button here, as we can evaluate it, it will evaluate as we'd expect here. This turns out to be, underneath, a button box. And likewise, if we've got these two dynamics, here's a nice, sort of semi-simple example of a dynamics. They're linked. We have, as we move the slider, the value of mn changes, and this dynamic here just represents that change. And we see underneath, our control is actually a slider box, and our dynamic here is a dynamic box. So everything in the front end is boxes. So it's very important that we can actually override this to actually allow and affect our own overriding of the notations in Mathematica. And I can now actually say that that's sort of my area that I work on in Wolfram Research. I'm sort of in charge of, along with John and everybody else that does it, the boxes. And so in the front end, the main front end, and then now in our new NB-like core. The locator's a box. Yep. So everything's boxes. So and in fact, yep, everything's based. Well, there's other stuff besides boxes. It's too much, but it's the language which you'll use to customize and everything you'll be dealing with the boxes. There's of course the styles on the style sheet. There's other, when you get a notebook expressions, you'll see cells and box data and notebooks and other stuff. But primarily the underlying bits as you interact is boxes. Okay, so the question is, when we evaluate stuff, what actually goes on? So if I take a look at some evaluation like this, I get the derivative of sine y over 2 is cosine y over 2. We all know that. What's actually happened as we go through here? So what happens is the front end basically has this list of boxes. It has this sort of box expression, and that needs to be sort of parsed into an actual kernel expression. And it's that those boxes are actually parsed into something a lot more like d of sine of y over 2 comma y. And that, of course, goes through evaluation to get something like cosine y over 2. And cosine y over 2, of course, then turns around and it's displayed in the front end back into a normal form in terms of boxes. So like that. So basically what's happening is we start off with this box structure, with this, which is this sine, this expression, partial y, sine y over 2, that gets parsed to a kernel expression, which is just this d of sine y over 2. That gets evaluated into this form, and then of course it gets displayed in terms of boxes back in the front end. So we start off with the box structure. We start off with the box structure. It isn't? It might be on Windows. Sorry. There's some, yeah, so, right. We'll fix that after. This box structure, it starts off with a box structure. It gets parsed into a kernel expression. And it happens via make expression. In other words, we take boxes, we make an expression from them to get a kernel expression. Evaluation occurs to get a new kernel expression. And then we go make boxes through formatting to get a new box structure. And so this is how we perceive formatting and parsing to occur, but it actually goes through the stage of going through the kernel. So the trick now is, so we've got parsing as make expression, we've got formatting as make boxes. We need to be able to override those, and if we can, then we can turn around and create our own notations. So let us start and actually do that. So this is our notation we were talking about. Escape PD, escape here, a plus, and something like a D. Mathematica doesn't understand that right now, and we want it to actually look like PD plus of V, which it does understand. So how do we do this? Well, we're going to do make expression, and on which boxes? So we're going to try and do make expression on these boxes, and so I use Command-Shift-E to get the boxes out of here on this in standard form, and right now Mathematica doesn't know what to do with those boxes. But it does know what to do with these boxes here. If I grab the boxes for the output here, and I do this make expression on those boxes in standard form, it does know what to do. So what we're going to do is we're going to tell Mathematica what this means in terms of boxes it does know how to work with, like so. And now this particular input will actually work. But of course, it's just for this input. If I change that to a Q, it still doesn't know what's going on because, of course, we haven't changed it here. So if I change that to a Q here and change this to a Q here, I now have something that works for Q underscore, for instance. We have something that works in general for Q or for T or for any, T cubed and so on. So now we've created the parsing. We've created a rule to make parsing work by rewriting the boxes that it doesn't understand in terms of boxes that it does know how to make an expression from. Okay, so that's good, but what happens, we want this to output as well. So we want this not to just be an input, we want this to be output. So we need now to have this form to work in the output. And so we need to be able to make expression on some expression like this. And we'll make this general for any t. And of course, I'm on a new MacBook, and the keys are a bit weird. I don't know if I like the touch bar. It's not so cool. But anyway, so the make expression of this, what kind of boxes is this going to be? Well, it's going to be those boxes here. We can copy them and, dang it, copy those boxes. It'll be this expression here. And of course, this t will be something like that. But of course, t is an expression, so it needs to be further made into boxes. So we need to call make boxes again on this, again, as follows. And now we have this working and parsing as, did I enter that? Oh, make boxes. Oh. There we go. Okay, and so this works, and it now has, of course, the right full form, as you'd expect, and it works with both input and output. Okay, and so there's the rules in the notebook that say exactly this. Now that, of course, it's a working and functioning notation, we can actually make a sort of, for instance, a linearity rule. Here's a linearity rule over this partial plus. It works as we'd expect, and it has the right full form. So just to summarize again, the make expression is we're taking boxes, and boxes that it doesn't know how to make, into boxes it does know how to make, and from the boxes, we're writing an expression in terms of boxes and the output. So that's the process of creating the notation. Let me just mention a few other things before I hand it over to the people in the audience. You can try this on your laptop, and we've got Lou and Aaron and Itai to actually help you if you've got any questions. And I'm going to give you some exercises. So if we have some input like this, plus y squared plus this pd plus of some t here, we can enter the notations sometimes linearly. And this is this trick that I mentioned in the talk. We can actually get a traditional form, a standard form, or an input form here just by cycling around by our various keys. And so it's sometimes useful to just enter it in linearly and then convert to standard form. And of course, this only works if the thing makes syntactic sense. If I put a plus on the end, for instance, that doesn't, Mathematica can't work with that. I can't convert it to different forms. So it's got to make syntactic sense. And one of the other things we sometimes do is put like a print of 2 in there. And so as we go around all the various different forms, we see it's not printing. So we're not leaking anything. Our typesetting, if there was a 2 appearing below, then some evaluation would be happening, which would be bad. Okay. So, right, on to this notation. This is your first exercise in this workshop. So here, this is built into Mathematica, a nice function notation. I like it. Looks, traditional mathematical form of a function, and it works in standard form. So that's good. It works, r plus t, something here, does what we want. But the function, so in other words, the make expression is working. It understands these boxes, but the formatting isn't working. Its output as function would like that to appear like the input. How do we do that? So we need a make boxes rule. That's your exercise. I'll give you a minute to think about that. Come on, Yi, you've got to be able to get it. Come on. Others? Stan, you probably know exactly. Oh, yeah. At least if you don't get it, at least you can start thinking about it, and then you see the answer, and then it'll hopefully go in. Yeah, so that's escape, function escape. Yeah, it's nice, isn't it? Yeah. Yep. So, yeah, no, it's been around. Yep. It's escape, function, escape. Well, you need to create your notation for right t arrow being a function. So, okay, so Yi, we're done? Almost? Okay, I'll go on with the answer here. So what we want is, of course, we want to make boxes. We want to be able to make boxes. In other words, we're given an expression, and our expression here is something like function a of t. We want to be able to make that into in standard form, and we want this to be any sort of parameter here, a parameter here, parameter here in standard form. And what should those boxes actually be? Well, they should be, if we went and copied that, yeah. We get those boxes and paste it in here. And of course, it's not going to be that. We need to make boxes of t, comma, standard form. And we also need, so in other words, we need to make both arguments here. This keyboard is really, the treble key, the treble stroke is actually different. John was asking me, did it make a difference? And I didn't really think so until today when I was practicing this. It really does make a difference. Okay, so we have some function that, yeah, really the escape key's in the wrong place, the treble, no, it's just all wrong. Yeah, you shouldn't have, yeah. So that works as we want, and it has the right, output, and it has the right full form as we've created here. Okay, So that's one example. Let's move on. Now that you've got that, and you've got this sort of simple example, let's move it down to up and down. So maybe we're dealing in physics, a spin glass or something else like that. We have an up arrow plus a B, down arrow, down arrow here, something else like that. And we want Mathematica to be able to understand that in terms of up of A plus down of B. Okay, so create the notation to go from one to the other. That's the task. Yee. Yeah.
Demo, which is where you start typing in typeset expressions and the boxes are shown.
Yep.
The inverse. So when you start typing make expressions,
Oh.
To show you what it's typed.
Yeah, yeah.
Would be
Yeah.
really useful because I can never get these right.
Sure.
Lots of work.
Yeah. Well, the whole trick is, of course, you copy the boxes that Mathematica puts in. So like whenever I'm creating my own notations, I never try and, is it a subscript? You just type it in, see it, and then you copy it.
It would be nice if there was a more elegant way out of the show expression to actually capture the, for example, bracket matching, so you could capture the boxes in a more elegant way, and it's always a hack.
Yeah, it does the bracket matching with Command-Shift-B, but yeah, it is a bit, right. Okay, so let's take a look at this particular example here. Let's do the first of all, let's make it parse. So right now that's not parsing, so we need make expression. What are the boxes that we're going to make parse? So we get here, get the actual boxes, the superscript box here with that in standard form. And what's it going to be? Well, it's just going to be, of course, make expression of the boxes for up of A, which it does know how to make. And so we grab that in standard form. And of course, this is not, dang it, this is not just A, this is of course any expression here, and that's just A. And of course now our expression works, our up of A works. Let's do the same one for down now. Same sort of rule. Down arrow, and of course this is just down. And now our whole expression parses as we want, but of course when we enter it again, it's not formatting. So we need now some make boxes rules, pretty simple. Make boxes rules, and what are we going to make? We're going to make, of course, up of A, whatever in standard form. Standard form is, what are the boxes for that? Well, we know what they are. They're these boxes here. Yep. Yeah. Yeah, it would. That would be really nice. Make boxes of A, comma, standard form, as we've got. And so the similar one for the down. Yeah, really. It's nice and fast, but yeah. So okay, and so finally now, our formatting is working as we'd want. It has plus Q, and it has the full form, the correct full form as we'd want. Okay, so that's parsing and formatting of the up and down spins. The next one would like to actually talk about is formatting of a matrix. So normally now a list of lists is considered a list of lists. In traditional form, it looks like a matrix. Input form, it's a list of lists. Standard form, a list of lists. And in traditional form, it's a matrix. So the question is, how do we, and of course, Mathematica understands this, so we don't need any parsing rules. We just need a formatting rule. How do we make Mathematica make this nice? How do we have a standard form that looks like a matrix? So create a make boxes rule to make a list of lists look like that. That's the next question. How would we do that? So at the beginning here, we're not going to worry about evaluation. So now we need something. So what we need to do, to do this, we need to basically take and make boxes over the various arguments that we've got. And so if we try a normal map, of course, it's not at quite the right level. We need it to map over each of the individual arguments. So we can turn around here and just map at a different level, like so. And of course, this is now, instead of that, it's going to be a make boxes of its argument, comma, in standard form function. That's what we're going to do over the various arguments. And of course, what is the actual output that we want it to look like? Well, we want it to look like this. Whew, big expression there, but let's just grab it anyways. Do the bracket matching, copy that. And so we want it to be these boxes here, but we don't want the grid box alignment option. We don't want the grid box spacings, so that's all fine. So we want it to look like that. The inner bit is what we're going to replace by this bit here. And replace this argument here by our A, and voila. That's what we want. And now as we see, we cycle to our input form, our traditional form, and our standard form, and it's sort of working, except you notice it's now 4. We had 2 plus 2, and as I go to a standard form, traditional form, but as a traditional form and input form, but as we go to standard form there, it's evaluated. We've got a leak. We've got an evaluation leak, which is bad. We don't want to do this. Itai said it's bad. I think it's bad. It's bad. So how do we get around this? Well, we've got to worry about evaluation. And so here, if we take a look at what's being evaluated, you've got to be very careful. Evaluation slips in lots of places. It'll slip in here at the matrix Q. It'll slip in at the application of this function. This needs to be a pure function with a hold all, and it needs to be unevaluated on this argument. And so I can turn around and put here matrix Q of unevaluated of A, and make sure my function here that I'm mapping over here is actually go back to a function, go here, make it a function of like B, some variable here, B, come here at the end, and make sure it's hold all. And of course, we need an unevaluated around here, like that. And so that, I think, gets rid of all the evaluation stuff. We're going to turn around and quit our kernel just to make sure that we don't have previous rules there. Go here, and now go back up and try 2 plus 2, input, traditional, normal form, the standard form. Whoa. So we've done it. We've done it. And so right now, as we have any particular matrix in standard form, we enter it, control, A, Q, something else. It'll appear as a matrix in our output form. Okay. So again, through a make boxes rule. And so that gives you an idea about the holding. I'll talk briefly about tag boxes. Tag boxes, as we mentioned, these are invisible boxes that go in the typesetting structures that appear there. So for instance, here in this output, when I enter that again, in fact, let me just get rid of our notations, everything we've added before, quit that, we enter that, we actually get in the output a matrix. We don't get a list of lists anymore. And so you wonder, well, how did this happen? How do we get this list of lists? Not get a list of lists, and it's because underneath there's this tag box. So this grid box here is wrapped in this tag box. So, and that tag box, when make expression takes a look at that and says, oh, there's this box, there's a tag box thing. I'm not going to make it into a list of lists. I'm going to make it into a grid. So we can actually turn around and even just delete that grid right there, and it'll come back and be formatted as a list of lists. So here, there's this invisible tag box underneath, and here the tag box is gone, and we've got a list of lists. Other than that, we've since moved on from tag boxes as a major source of typesetting. It's now moved on to template boxes. They are used if we take a look at a function template here, tabbing through them and so on. We've got tag boxes in there, and they're used in like mouse appearance, and as we move over the mouse, there's a tag box in there and manipulates in some of the other places. But we won't talk about that too much. Okay, so now I'd like to talk about the notation package. What's it useful for? Well, creating these notations, these make boxes and make expressions, it's kind of hard sometimes to get things in the right places. So let's take a look at this one example I've got here. This ring plus and ring times doesn't actually work. So how do we create a notation for that? We could go to the notation palette here and paste a notation. And this is the external boxes, a underscore plus, and we do escape, get our ring plus operator there. And that's the external thing we're trying to recognize, and that's going to be recognized as a ring plus of a underscore comma b underscore, like so. And so that, if we do the same thing now for our multiplication, we see a ring times here. And now this thing will parse and format. It has the right parsing and the right formatting. And so what happens is these notation statements are basically, you can think of it as a transpiler. We're taking these rules, these box rules, and we're creating, the notation package creates equivalent make boxes and make expression rules to actually to affect the notation that you're trying to work with. So the one goes both ways. It's just one is just, in fact, let me just quit that. And actually turn around the kernel. I'm going to quit this. There is ways to remove the particular notations, but I won't go into that. And so here we have it formatting, and it doesn't understand it at all. If we take a look at this, I think that is just double long right arrow. And we go here and have this is a double long right arrow, just the one way. So now we enter the notations for that. We will see the ring plus will format as a ring plus, but ring times will not format. So in other words, by this arrow, it directs it, what are the different directions that we're doing. So right now from here, we can see it'll actually parse into this expression, but here it'll parse and it'll format. Yep. Exactly. This is a compiler. This is basically, the notation statement basically turns around and it compiles that into rules for make expression and make boxes. And in fact, let me show you here. Let me get exactly this. Go to here and type action. Print notation rules. And we can actually see one of them. And so these rules, this is the rules the notation package is actually generating. And it's quite similar. It says notation make expression instead of make expression, and there's some of the notation backtick private gunk. But other than that, it's sort of like a make expression equals make expression of something else. And we've got this ring plus operator here. So it's rewriting this in something which it doesn't understand into something it does, and likewise make boxes. And so this notation statement is generating these rules, which Mathematica then uses to affect the notations. And so you can study these output rules, which is kind of useful to actually see what's going on. Indeed. Yeah, that's a good point here. So normally, you don't actually see underscores on both sides. You just see it on sort of the one side. But when I designed it, when I put this in, it seemed right to me. And since it's going back and forth, I've put it in on both sides. Yep. OK. And so one of the other things you'll actually see in here as well, you'll see instead of make boxes, here's the notation make boxes. Instead of here being make boxes, it's actually parenthesize. And so that gets the right parenthesize is actually a generalization of make boxes, but I won't go too much into the details, but it makes sure everything has the right brackets around it and looks good. OK. So one of the other things I wanted to mention here in terms of complexities to do with this is that if we have a normal A times B plus C plus D, and I look at that in terms of full forms, we'll actually see it's parsed flat. We have a plus times AB, and then we've got a C comma D here. So here with our rules that we're actually doing, with our notation rules here, we're not actually parsing flat. If I get this here, put that in, put a D here, and actually take a look at the full form of all of that, we'll see we parse the ring times instead of the times in the same way, but there's a ring plus, and then there's an outer ring plus. Sometimes we want that to be actually flat. We want a flat operator. So to actually do that, instead of our notations here that we've actually got, we can turn around and put in an infix notation. So we do this via the following, and of course would turn around and make our ring plus be an infix notation for ring plus. And similarly, we do ring times, and now our structure, instead of, I didn't evaluate the kernel. Yep, got to do that. Yeah. Right. And now, we have the same form. Our times, our ring times is parsed flat, and our ring plus has parsed flat exactly like the normal bits internally to Mathematica. Okay. So as an exercise in actually using this, it might be you can turn around and create, again, your up and down notations using the notation package. It's not that hard. I'll give you a second to try that right there. Yee. Okay, so we want some of the A with the up arrow here was be A of underscore, put an underscore on the other side, as we've got here, and similarly, down arrow is down, and now we've got the notations we want up of A plus down of R and standard form. And they work, they parse, and they work as you'd expect. Okay, so to quickly enter notations as well, Itai mentioned the fact that you've got these various input aliases that you can actually use. Adding them in Mathematica with the notation package is actually quite easy. You just give it a short form, you give it the various boxes, and now we can do escape, add input alias, escape, to add our own. And of course, if we wanted to actually use this one here, this OPU, we can just type escape, OPU, escape, and we've got the boxes and it does what we want and it has the right full form, etc. So adding our own full forms like the limits or the other things that you saw Itai use is quite easy. And so, yep. Bug. It's been one of those things that's on my radar for ages, but it probably falls to Aaron now. Okay. Right. Cool. Okay. So one of the other things we need to mention before we mention template boxes is base styles. So normally, in fact, in a normal text editor, is if I start typing in a normal cell and that cell is italic, and I just click off there and click next to it and start typing again, I get italic. And so it sort of captures the style. That's traditional of what happens. And so if I have a style box, the same thing happens here. So this is raw boxes. And raw boxes, I don't know if I've used raw boxes before. If I enter it here as style, if I enter a box expression, it's just a normal expression in the kernel. The kernel can deal with it. In fact, we make use of being able to deal with it in the whole... This is an 11.2. I hit some weird key combination. I think it was this Mac is decidedly annoying. Base styles. Here we go. So the raw boxes just takes that and puts the boxes as an output expression here. And so you see it's just outputted this as the boxes. But if we type right next to that, we see it's actually captured the style, which is not exactly what we want. We want to be able to create typesetting units that are self-contained, that are completely encapsulated. And here, if we do this, we can actually see with this, by using this base style, we can include whatever styles, font sizes, magnifications, whatever we want in the particular style. And then right next to it, they're constrained to just that particular box. So that's something very useful, which we're about to make use of. In the base style, in the default base style, John and I added that. I'm not too sure. a while ago, and it's in most boxes that are around. Almost all your boxes will have that as an option. Okay, so now we get to this template boxes that Itai was talking about, and how we can use those and influence our typesetting with them. So let's actually talk about them right now. So here we have a binomial of n comma k in traditional form. So you've seen this grid box before. You probably think this is a grid box with some brackets. And when I take a look at the underlying boxes, we're going to see something like that. But actually, we don't. We see this form box of a template box with these two arguments, n comma k, and this binomial thing. It's like, what? How is that looking like the binomial that we actually see? In fact, if I go in and I change them here, to change that to an m, evaluate it, it evaluates to the right thing. So somehow, just through the name of this binomial here, and the various arguments, it gets the right formatting, and it gets the right evaluation. So knowing that, why don't we actually even just change this? Let's just be a little bit tricky. Change that to a Bessel J, and it looks like a Bessel J function. We evaluate it. It even evaluates like a Bessel J. If we go in here and change that to a Bessel K, again, it evaluates like a Bessel K, or you could go in here, change it to, if I can type correctly, Legendre P. Yeah, we get a Legendre P function, and it works as one would expect. And of course, it has the right tooltip, and we can, as a template, we can't actually select the P. We can select the K or the M, and it works as we put this in. It deletes the various arguments. We tab back and forth between them, and it works as would sort of expect. Okay, so how is this actually working underneath? Let's actually talk now about this template boxes. So here, I've got a template box. I'm going to display it. I've got this. It's got two arguments, A and B, and it's got this weirdo tag, foo Legendre P, just sort of made it up. But it's got this display function that Itai talked about. So what I can do is I can actually take that display function here, and I can take a look, and we can apply it to the arguments of the template box here, and it gives another box expression. So that, in terms of our full form here, with the display function applied to the arguments of the template box, gives another complete box. And if we take a look at that in terms of raw boxes, it has an output. And indeed, that's exactly how the template box will display. So what happens is the template box, as it needs to know, how do I display this function? It goes and it gets the arguments, it plugs them into this display function here to get another box expression, and that's how the output of our template box actually looks. So it's integral part as a display function to determine how our template boxes actually look. And it's got this foo Legendre P tag here, and that, right now, indicates how the thing is actually evaluates. If we evaluate that, all of a sudden it gives this foo Legendre P. I could have changed this to Quidditch, for instance, or some bad spelling of it, and of course it will evaluate as Quidditch of A comma B. So this here, it's already got a built-in make expression rule for how this should actually work from these boxes. It just applies this function on the head of the two arguments. So that's great. So now all we need to do is actually change our display functions and get it to work with the right display functions to make the changes that we actually want. So let's go back here, get a binomial, add Q to it, get some other binomial, get that in traditional form, and take a look at now changing our binomials. So we can go here to the style sheet and actually figure out where is our binomial. On your style sheet, you'll find here, we'll go to the core, we find binomial, and we see it down here. It's really small, so I'm just going to copy that, go back here, paste it in here, close that section again, and go to 200%. And now we can actually see with the binomial what is the display function. And now we can see where the brackets come from and our grid box comes. And so our grid box and our brackets come from this current display function for the binomial, so we can change this to whatever display function we actually want. Let's take a look at C, N, choose things, N, K, something else like that. And of course, we just grab this function, we grab the boxes for that, the subscript box, and we're going to plug it in to our display function here. And so we do that, plug it in, change this to be, it's got to be a function that returns boxes. So that's the first argument. Here, this is the second argument. And now when I hit Command-Shift-E, we're going to see all of our binomials change to our CNK notation. And indeed, they did. So this, of course, this is still just a template box. So if I copy this and I get a new notebook and blow it up at 200%, I'm copying the template box. So in this style sheet, I don't have the new notation. So of course, it's just a binomial. So if I can take that now, go back here, edit this to be an R, come back, copy that, paste it back into this notebook, and I get back the notation in this notebook. So really, the template box on the style sheet is guiding via the display function how all of these things should actually look and behave. Okay, and so that's the power of template boxes. So let's actually state a bit more formally what a template box is. A template box, basically, it's a box. It has these box arguments, and it has this tag. And normally the tag is a string. And way back when, we made it so that if the tag is a string, it'll look on the style sheet, see if it has a style of that name, and it'll use those options. So it's using the display function, and that display function will plug in the box arguments, get a generated box, and use it and display it in that way. Okay, and so the template boxes here can be nested. They work as we'd expect. They have the nice tooltips, and now it only remains to make expression for these particular rules. So here's an example. Your last exercise in the remaining 9 minutes before questions, or including questions, I think. We have a my commutator. In physics, if we have a commutator is something a dot b minus b dot a is a typical thing in physics with operators. And so here's a my commutator. It has a display function built in, and luckily, right on the style sheet, we actually have this display function for a my commutator. So you could possibly change it or not, but because it's on the style sheet, we can actually get that display function right there, and we can actually get rid of it, and we will get the exact same form. It has the right input form, and it outputs as my commutator. So it parses, it works, it's got a nice tooltip. Your job is to write a make boxes rule so that this input of my commutator will have a nice output. Back to my commutator here. Yee. Following. So basically, this is the exact same trick from before. So we can add a make boxes rule, and we want to make boxes for a my commutator object here on A and B, and standard form to be equal to what are the boxes we want? Well, we want it to be these boxes here, so we want it to be this template box. And so we put that in. And this of course has to be make boxes of A, comma, standard form. In the same way with B here. And there is our rule now. We can parse, format, all of the various things appear as it should. We can go back here, get the input form, change it, T, Q, and so on, and it actually works. And so now we can make some sort of linearity rules if we want. For instance, in commutators, it's common that they're linear in their first arguments here, so we make that as A plus A underscore plus W underscore, and Q is equal to this thing we've got here, A, Q plus W, and so we see it. That's our linearity rule that we're adding, and so we've evaluated that, and now we can come in here and Q plus R plus T, with respect to Y or something, we get some linearity, as we'd expect. Okay. The one final thing to mention is that the interpretation function allows us, it's automatic, and so it wraps the style name around the particular arguments, and so we can actually copy these complex template box structures and put them on emails or something else, and it nicely will format them according to, again, our rules. So they're great. They work nicely for intercommunication, and they're fantastic. And in fact, most of the normal typesetting that Lou and Itai and everybody else does now, all our modern, special functions and other things are all done through template boxes. Okay, I've run out of time a little bit, so I won't mention the syntax form options. I will mention that graphics, of course, is context sensitive in its typesetting. The graphics, of course, here we've got a point, just typesets as just the expression, but inside of graphics, it's a point box. Okay, and one other interesting note is that, in fact, our whole typesetting model is being developed independently, of course, of CSS. But interestingly, all of the box model is very similar. Our image margins, our frame margins are similar to margins and padding, and a lot of the concepts from style sheets are somewhat the same. I don't think the CSS HTML guys copied us. We certainly didn't copy them, but it's interesting to see that there's some natural underlying sort of structure that we've converged on the same or close to the same sorts of models on underlying the way things work. Okay, so to create a template box notation, you first enter a structure in 2D, you copy the boxes into display function, put it on the style sheet, create a make boxes rule, and maybe for bonus points, create an input alias for the notation. I know this has come probably quite thick and fast. If you haven't seen this before, it's a whoomph of information, but at the same time, it gives you an idea, an outline of the steps that are needed, and hopefully you can go away and play with it a little bit to actually get your notations. It's not, as you see I'm doing it live, it's not that hard to actually do your own notations, and so you can create them and then use them in your field of study. Okay, that's it.